In this video, I am going to go over the rest of the efficiency problems, and they are on page 41. Now, a lot of the problems on page 41, we're going to end up using this power equation, this idea here. So that's what we'll probably use a lot of the times, other than the efficiency ones shown at the top of this list. All right, so I'm going to go to that page. Page 40 I did in a previous video, so if you have to, you can watch that one. All right, for number 11, a light bulb is rated at 40 watts. Now that is giving us the power. And it wants to know how much electrical energy does this bulb use in 1 second. So when it asks for how much electrical energy, that is asking us for work. The equation is power equals work. And on that previous page, it had it listed different ways. I'm just gonna write down how it had it. Work, energy change divided by time. So what we have to do is rearrange this for work. So for that, you get work equals power times time, which you get the 40 watts times 1 second, and that's going to give you 40 joules. The reason why you get 40 joules as your answer is because watt you can also think of as the joules per second. So the seconds will cancel out and you'll be left with joules. So that's telling us 40 joules. That's how much electrical energy the bulb uses in 1 second. Now B is asking us what is the efficiency if out of that 40 joules, only 5 joules is used to produce light. So for efficiency, we have the useful energy out divided by the total energy in. So in this, and then that's going to be, well, it's not asking us percent right now. That's actually going to come up in the next one. So we have that 5 joules. That is the useful light. The total energy that we figured out in the previous problem was at 40 joules. So that's giving us an efficiency of 0.125. Now this problem broke this apart into 2 different things. Now it's asking the percent efficiency. So now we take that 0.125, multiply it by 100, and that gives us 12.5%. The useful power output of the light bulb. So now key thing here is that it's saying useful. So the useful power, what we have to do is look at the useful work and divide it by the time. The useful work in this case, since we're talking about a light bulb, the useful work is this 5 joules of light. So that's what we're going to put up top. And that does not look like a 5. And that is divided by that 1 second. And that gives us useful power is 5 watts. Now, E is asking us how much light energy should the bulb give out in 3 minutes. Well, what we end up having here is we could do the power equals the work divided by time, and it's asking us for how much light, so this useful work output. And what we end up doing is rearranging the useful work equation, and that gives us power times time. So you have the 5 watts, what I'll write as joules per second instead of a watt, and that gets multiplied by, it's 3 minutes, but we need it in seconds. This is why I wrote it as joules per second. 3 minutes is 180 seconds. So you do 5 joules per second multiplied by 180 seconds. The seconds cancel out, and that gives us the useful work output, so 900 joules of light. Now F is asking us how much heat energy should the bulb give out in 3 minutes. So what we're looking at is the total energy for this light bulb ends up being the useful energy, which I will write as light, plus the energy given off as heat. So the total energy we know is 40 watts. The light energy we know is 5 watts. What we don't know right now is the heat energy. So you just do a little bit of subtraction, and the heat ends up being 35 watts. And remember, watt is a joules per second. So what it's asking is how much heat energy should the bulb give out in 3 minutes? Remember, when you're doing this, it's power multiplied by time. Now, what we end up using is this 35 watts as the power, and I'm writing that as joules per second. The time is 3 minutes, so again, that's 180 seconds because we need the seconds to cancel out. And then that gives us 6,300 joules in 3 minutes. So when you look at the numbers for this light bulb, it gives off 900 joules of light, but 6,300 joules of heat energy. So it's not very efficient, but that's what we use with those numbers there, with that light bulb. That's what we get. All right, going to scroll down to number 12. An electric motor pulls a mass of 4 kilograms up by 3 meters in 5 seconds when supplied with 360 joules of electrical energy. Now this one's going to ask us for a couple things: weight, work, power, percentage, power supplied. So when we're doing this, pay attention to all these units here. Well, it tells us that this 4 kilograms is the mass, the 3 meters is the distance, 5 seconds is the time, supplied with 360 joules. So that 360 joules, that is energy input. That's how much energy was put into that thing. So the weight of the mass, remember, if we talk about weight, what you end up doing is mass times gravity. The mass is 4 kilograms, gravity is 9.8 meters per second squared, and you end up getting 39.2 kilograms meters per second squared, which is the same as a newton, so 39.2 newtons. Remember, a newton is how much force it takes to move a 1 kilogram object by 1 meter per second squared, or get it to accelerate by 1 meter per second squared. So when you have kilograms meters per second squared, that's the same as a newton. Now, how much work does this motor do? Work is force times distance, and we just figured out the force, 39.2 newtons. The distance was 3 meters. So now you get the units of newton meters, which is the same as a joule, and when you do that multiplication, you get 117.6 joules. Now it's asking the power of the motor. Power is work divided by time. Oh, that looks a little sloppy there. I'm hitting buttons on my pen. All right, power is work divided by time. So we have the 117.6 joules. The time it gave us in the problem was 5 seconds. So that gives us 23.52 watts. The percent efficiency of the motor. Okay, well now we have to look at the equation for efficiency. It is useful energy out divided by total energy in, and we'll end up multiplying that by 100. So what we have to do is make sure we use the right numbers. The useful energy out was this 117.6 joules that we calculated. The total energy in was given in the problem. That's at 360 joules. And then we're going to multiply our answer by 100, and that gives us 32.67% efficiency. There's a decimal point there. Now, the power supplied to the motor. So what we have to look at for power supplied, it's the energy supplied divided by the time. So the energy supplied, according to the problem, was 360 joules. And the time was 5 seconds. So that gives us 72 watts. All right, so energy supplied was 72 watts. The power of the motor, the output basically is 23.52 watts. And they're the numbers we're working with, right? Which makes sense because it's only about 33% efficient. All right, the last problem, number 13. Runner has a mass of 120 kilograms, maintains a speed of 5 meters per second while using chemical energy from food at a rate of 4,500 joules per second. All right, so kinetic energy is 1/2 mv squared. You have 1/2 times the 120 kilograms times the 5 meters per second, and that is the part getting squared. So when you do all that math, kinetic energy ends up being 1,500 joules. The input power from the food. So when we look at input power, the way it's worded on page 20, we could just use that wording, energy change divided by time. So we take the input power. So what we have to look at is the energy being input, which is at 4,500 joules, right? Because that is the energy input from the food, the chemical energy. So you do that division and you get 4,500 watts. And now the efficiency just like we have been doing, useful energy out, which is in this case 1,500 joules, this one, divided by the total energy in, which was this 4,500 joules. That's the energy in due to the chemical energy stored in the food. We're going to multiply our answer by 100%, and that gives us 33%. So my guess is a lot of that energy is being, well, wasted, I guess you could say, through sweating.